Right, it's 6:30 p.m. IST. It's time to start. So first of all, good morning, good afternoon, good evening to each and every one of you who has been able to make time to join this presentation today. I'm pretty much aware that every one of us is really excited to hear something very interesting today, especially since we are looking at the highest arch bridge in the world, and we are going to talk about it. We have experts to talk about it from Afcons, and I really thank Afcons team to do this for IC. Before we commence with the main presentation, I would like to take you through various things that IC is doing in Mumbai. I am the regional representative of IC, and I'm pretty glad to do a very quick introduction about IC in Mumbai as well. Today's session is extremely interesting. We have received entries and registrations from people, professionals across the globe, across 21 countries, in fact, and I'm really thrilled to note the kind of interest this particular event has generated. I hope to continue the same zeal going forward into next sessions that we will be hosting under the ICE Mumbai Genesis template. So again, thanks a lot for the patronage we have seen so far. We have tried to be as diverse in terms of the topics we bring in through this platform, and I'm I'm absolutely enthused looking at the response that we have received so far. Talking about ICE and IC in Mumbai, as you probably, a lot of you know, IC is the Institute of Civil Engineers based out of UK, has a significantly large global professional base present and is present across 162 countries. One of the oldest organizations as far as civil engineers or a conglomerate of civil engineers is concerned, with a very, very keen focus on improving the quality of civil engineering per se, support all the supporting systems, all the knowledge that exists within civil engineering is actually available through the IC platform. And there are multiple ways in which professionals can connect to ICE, apart from just becoming members. And I think one of this kind of event is such where each and every civil engineer is absolutely welcome and be a part of IC and learn from what civil engineering is all about. As far as various aspects of or offerings of the Institute of Civil Engineers concerned, apart from being a platform for civil engineers, there are some very interesting resources available on the platform itself, which you are all able to see on your screen. Learning Hub, then there are various libraries actually available, recorded videos of a lot of events that happen within the ICE platform across the globe. They are also recorded and they are available on the IC website for professionals to gain knowledge from and gain expertise and share their expertise and so on and so forth. So feel free to reach out to the IC website. I'm quite sure there is a huge quantum of data, information, knowledge available through the IC portal itself. NCE, the New Civil Engineer magazine, is again internationally reputed, extremely well received magazine, which is also a part of the IC platform itself. Apart from various other rewards that are given to encourage people embrace civil engineering as a profession for their life. IC also provides a lot of support through the IC Benevolent Fund, and a lot of information is actually available on the IC website. So feel free to look into the website. If you have any questions, feel free to reach out to me. I'll be providing my coordinates towards the end of my presentation. How can you be a part of IC? You can be a part of IC right across your civil engineering lifespan, starting from your college as a student member to being a full member, a chartered member of the institution, or being a technician member in case you are a CAD designer regularly working in the civil engineering industry or linked with civil engineering industry in some way or the other. Or you can be a full chartered member, or you can also be a fellow member. Fellow member is obviously the highest membership level that's actually existent within IC. As a IC representative for the Mumbai regional for the Mumbai region, I'm extremely proud to have an extremely illustrious set of team members who are my committee members, and I think I do take a lot of advice from each one of these. They are all significant contributors to what IC does within Mumbai. Obviously, we are all currently limited with the quantum of movement that we can have, and therefore limited to primarily activities related to virtual sessions like the one that you're witnessing right now. But we hope to, as things sort of get better, as things are relaxed, I'm quite hopeful that we should be able to commence with some other activities which could be outdoors as well. So those are the kind of activities that we have done so far. I'm very proud that we have been able to benefit a lot of engineers across the globe. You know, for example, some of the sessions that we have done, we did nearly 26 Genesis Tech Talks last year, which was witnessed by more than 1,000 professionals across the globe. So I'm really proud about having been able to spread the knowledge, create the awareness, bring more engagement within the civil engineering fraternity, and bring everybody linked through a common platform of IC to engage, share views, share ideas, share knowledge, and therefore each one of us gains in some way or the other. Those are my coordinates. I'm based out of Mumbai. That is my email address. I'm also a part of the mentors, and there are 4 mentors available in the region. Professionals who are very keen to become members and want to pursue professional qualifications like the charterships, the incorporated engineers, and so on and so forth, or even become fellows. Feel free to reach out to me or the IC website itself, and you'll be able to seek a lot of guidance from both. And in case you need any mentor, the mentor support is actually available within the IC Mumbai region itself, and we should be able to link you with some or the other mentor who can help you understand the professional qualification processes, get you linked up with the right people, with the right resources, and make sure that you're able to work your way to becoming a chartered professional, which obviously has global appreciation. Right. So with that brief discussion on ICE, I'm extremely happy and extremely proud to invite and extremely privileged, in fact, to invite Mr. Giridhar Rajgopalan, who is Deputy Managing Director at Afcons Infrastructure Limited. Obviously, we have already shared his credentials. I think his CV looks simply amazing. I'm just as eager as each one of you to really hear him out today. And I'm extremely thankful to him and his entire Afcons team to express willingness to share their experience through building a structure which today is a world icon. I'm very sure that we have a lot to learn from today's session. So with that brief, Mr. Giridhar, if you could switch on your video, I will pause my presentation and over to you.
So am I audible now?
Yes, you're audible, Giridhar. Yeah. So just a quick, I just like to make sure that, I also introduce my colleague Ajit Savdi, who's the chairman of IC Mumbai region. And there's something that has come up very urgently, which I need to attend to, and therefore I'll have to drop out. But from here on, Ajit will be coordinating and sort of closing this session for us. So thanks a lot, Ajit, for doing this. And over to you, Mr. Giridhar.
Thank you very much, Mr. Rajesh, for your kind introduction. It's also a honor and a privilege that you have given Afcons and myself this platform to portray and present the iconic project Chenna Bridge. Before I get into it, I also heard you say that we have people from nearly 21 countries attending. So let me first invite them by saying a good morning to the people in the Western Hemisphere, good afternoon to people in Europe, a good evening to the people in India, and a late good evening to the people in the Far East. Without too much of detail, let me take you into my presentation. Just to cross check, is my presentation now available on the screen?
Yes, it is.
Thank you. Let me make it full screen. Right. So once again, thank you and a warm welcome to all to join this Mumbai Genesis 50. I will be talking about fabrication and erection of the steel arch for the world's highest railway bridge once completed. Before I start, I would like to share some insights about the group to which Afcons belongs. Afcons is a part of the Shapurji Palanji group. It's been a part of this group from 2000. Afcons itself was born in 1959. We are about 62 years young, and we have a very strong EPC and construction background. We work in 5 verticals: marine and industrial, surface transport, urban infrastructure, oil and gas, hydro and underground, carrying out a gamut of engineering projects which are not only challenging, but in some cases extreme in our projects. That's a small nutshell about Afcons. Without wasting too much time, let me dive straight away into the project. Let's look at Chenna Bridge. Once completed, it would be the world's highest railway bridge. It's being built to link Udhampur, Srinagar, Barmula as a rail link project. It is situated in the Himalayas, which is called a very active and young mountain. It has sub-zero temperatures, a very difficult accessibility to the location, a sensitive border area. These particular things made us look at ways and means to carry out that project, and there was a great need to look at newer technologies and innovations in order to execute this project. Incidentally, this project is at an altitude of 840 meters. What I would take you today through is a brief introduction to the Chenna Bridge, the details of the arch, the planning of the different elements, including the cable crane, trial assembly, lifting of the different members, transportation and erection of the wind bracings, global and local erection cycles, stressing of the say cables, geometry control, arch closure, and then the safety challenges that we faced, the other challenges we faced, and what we have now foreseen as the factors that led to the success of a successful closure of the arch. So let me start by introducing the Chenna Bridge. Before I start the Chenna Bridge, let me introduce the key stakeholders. Clients are Northern Railway and Konkan Railway Corporation Limited. Contractor is Chenna Bridge Undertaking, which is an undertaking of Afcons Infrastructure Limited. Design consultants are WSP Finland and Leonard Andre and Partners Germany. Proof consultants comprises of Scott Wilson Kirkpatrick and Company England, Scott Wilson Kirkpatrick India, Flint and Neil London. They are now called AECOM and COVI since they were taken over. The slope stabilization part of this project was handled by IISc Bangalore, IIT Delhi, and Itasca USA. Last but not the least was the enabling work design, which to a large extent was done in-house by Afcons Infrastructure Limited. The key to this project was the planning, which we will discuss in greater detail as we go more into the project. To give you a snapshot of this project, you can see the link between Udhampur to Barmula. The blue portions of the project are the portions which are already completed and are more or less on, whereas the red portion, which is in the difficult part of the hills, is under construction. Chenna Bridge is at about 125 kilometers from Jammu, and one of the most important challenges was the accessibility to the project. The nearest location, which is Riyasi, up to which 40-foot trailers could go, had to be made as a transshipment point for all our materials, including our equipments. Our equipments had to be then transported from Riyasi to the project site in knockdown condition, reassembled and commissioned. I will show you the general arrangement. The key features are the total length is about 1,315 meters. It's about 365 meters above the high flood level. The arch span is about 467 meters, and the viaduct had both a transition and a circular curve, which was in itself a unique challenge. It was about 35 meters taller than the Eiffel Tower if we want to compare it with the Eiffel Tower. This is another view of the arch of the bridge elevation. The arch portion with the arch of 467 meters had a superstructure of 785 meters and a viaduct of 530 meters. Very important to note that the expansion joints that are likely to be provided in this project have movements of plus minus 800 millimeters, probably quite large in the context of Indian bridges. There is something which I have now put on the slide, which is circled. These are the locations of the pylon which supported the cable crane, and the locations of this was one of the key in making the arch erection a very great success. Later, when I take you through the erection, you will understand the importance of these locations. Some of the main highlights of the Chenab Bridge in a nutshell are: it's the world's highest railway bridge once completed. It has a design life of 120 years. We have done an incremental launching of the deck superstructure on the viaduct, which had a combined circular and transition curve, the first time in the world. World's largest capacity crossbar cable crane has been used for erection. Extensive wind tunnel testing was carried out, first time in India for this project. Fatigue designing and detailing of the bridge was again carried out for the first time in India. Installation of double corrosion protected bars and cable anchors also done for the first time in India. And we have used 10.9 grade, one of the largest diameters available in this grade, M36, with a geomit coating to ensure durability of the bolts. The design was blast resistant. Some of the key other considerations were the geographical location of the project. It's in the snow-clad Himalaya mountains, near zero temperature, so we needed to adopt very special structural steel. Highly active seismic zone, so hence site-specific response spectrum had to be deployed. Dynamic analysis of the structure and ductile detailing was also the need of the hour. The geological conditions also proved to be a challenge. We did very detailed geotechnical and geological investigations and extensive slope stability analysis. High wind speeds are prone in this area, so this bridge is designed that if the wind speeds exceed 90 km per hour, the trains would be stopped. The design generally was based on the outputs from the wind tunnel tests. Further, this being in a very sensitive border area, the bridge was designed with some redundancy. Even if one pier of the bridge is collapsed, the bridge would still stand under its self-weight. Further, when it came to the arch, we could actually remove one of the cord member, but still the bridge would be stable and it could still continue to carry traffic at a restricted speed. No doubt, the speed restrictions would continue till this damaged cord is reassembled. Similarly, one of the vertical diagonal members could get dislodged, but still the same parameter of the bridge being stable and still being able to carry traffic at a restricted speed would be possible. So these are the special considerations under which this bridge has been designed. To give you an overall picture of the scope of the work, we had about 1 million cubic meters of excavation. Concreting was to the tune of about 73,000 cubic meters. Shotcreting to the tune of about 76,000 square meters. Rock bolting of nearly 90 kilometers. Fabrication and erection of structural steel of 30,000 plus tonnage. And the most important, installation of HSFG bolts of 3,06,312 numbers. What is not shown on this slide is the consolidation grouting that needed to be done on both the banks, which in itself could be a paper for presentation. This area has highly fissured rock, and hence it needed about 23,400 metric tons of cement to be used to grout it. Highly fissured rock, need of the hour was to come to a fine point of ascertaining the pressure at which it has to be grouted. This in itself was a technical challenge. A lot of trials were carried out to ascertain the right pressure for grouting. When we go to the viaduct, this was the viaduct which we did on a combined transition and circular curve. First time in the world. This in itself was a great challenge. But what was very satisfying for us at the end of it was that we started the transition and the circular curve launching from P180, which you can see on the far right of the slide. And we went pushing this up to somewhere in between P120 and 130. Then we did the straight launching from P80 towards P120. But what was most important was that when both these met with each other, the lateral adjustment that needed to be done was only 3 millimeter. I repeat, 3 millimeter, which was the accuracy that we were able to achieve by proper guidance mechanism. Next, I will take you through some of the slope stabilization photographs. On the left, you are now seeing the slope of one of these sites, which is the left bank. Excavation was to the tune of about 6.3 lakh cubic meters. Rock bolting was around 33,000 running meters. Shotcreting was 55,000 square meters. And Viaduct bars were about 4,000 running meters. This was before excavation. So when we really looked at it and we went there the first time, there was a lot of wonder in us whether we could carve out this hill and create the foundations. I'll now take you through the right photograph. This is how it looked after we carved out the hill, carried out the slope stabilization, and located the foundations, starting with S10 abutment, S20, S30, and S40, which in itself is a gigantic structure supporting the base of the arch. The total vertical excavation was 215 meters with the slope angles of nearly 70 degrees between the berms. And this was a very, very crucial element to ensure the start of the arch erection. A few photographs of the same. This is a view of the same left bank after a partially erected arch. This is another view of the right bank now. Similar types of excavation was carried out here. Another view of partially erected arch on the right bank. And that is all about the slope part of this project. What I would like to share here is that after the arch foundation was constructed, there was a pier that was erected on this arch foundation. This structural steel pier was 145 meters from the ground level. And what we could achieve was a great tolerance when it was finally erected. This slide shows you that the designers had permitted a tolerance of 100 mm in any direction. This complete pier had HSFG bolts of 10,512 numbers. Bolt hole clearance was 2 mm. What I mean by bolt hole clearance of 2 mm is, if there was a 32 mm dia bolt, the hole that was drilled was only 34 mm. With this sort of tight tolerances, we were finally able to erect. And when we located the pier cap at the top, you can see the tolerances that we have achieved. To the left of the slide, it had moved by 23 millimeters and 14 millimeters. On the direction of the bridge, about 14 and 19 millimeters. And in terms of level, about 23 millimeters. This accuracy was only possible with meticulous planning and a great amount of detail in erection. This is one part of our success. I'm just showing you a completed arch so that you get an idea of how the arch looked. Previously, when I talked about the pier, you can see one of the piers that has been erected, on which you can see a red temporary pier that was put to help us hold the cables, which were temporary in nature. I will now take you through the details of the arch, which is the topic for the day. The arch span is 467 meters. Height above the springing level is about 136 meters. The arch had a horizontal alignment which was straight, a vertical alignment which was level. The arch shape was parabolic. The taper of the arch in the vertical plane was 4.23 degrees. The arch had fixed support conditions. The arch section had prefabricated boxes which were to be later filled with concrete after the arch is closed. Different grades of steel starting from E410C to E410 plus Z35 were used on this project. I would like to highlight here one thing. While all these materials are theoretically available in India, they are very rarely manufactured by the Indian steel parties. So a lot of input, proactive collaboration with the steel manufacturers had to happen right at the beginning to produce this steel of a right quality and grade. Next, we had HSFG bolted joints. All were 10.9 grade. The arch itself consumed 210,590 number of bolts. The diameters of the bolts ranged from 16 mm to 36 mm. The total quantity of steel was 10,619 metric ton, and the arch had a total of 1,375 components. Why we looked at 1,375 will be explained in the further slides. Let me now take you through the planning for the design and erection of arch, the first part, which is the cable crane and sizing of the members. We have deployed the world's largest crossbar cable crane with a payload capacity when it works in tandem of 34 metric ton. On the right, you can see the image of the cable cranes working in tandem with a tandem bar. The weight of this tandem crossbar itself was 6 metric ton. And the beauty of this cable crane is that it can be worked also individually with a capacity of 20 metric ton. So there were times where the left side cable crane was being used separately, sometimes the right side cable crane separately, and when the need arose, in tandem. The maximum weight of the arch component hence was driven by the capacity of the cable crane, which was 34 ton. When the designers and Afcons sat together, a lot of brainstorming was done, and that is why the arch was split up into 1,375 components, which could each be handled. No doubt, while they had 1,375 components, the total number of lifts were reduced by other means, which I will explain a little later. When we look at the important thing which I explained a little before, you can see that the left cable crane had a working range, the right cable crane had a working range, and there was an area in between which could not be accessed by the cable crane. So to access those areas or greater weights, there was a need to combine the cable crane and use the crossbar, thereby not only covering the total width, but also having overlap to help us handle the project easily. We will now look at one of the important components, that is the trial assembly, which we did. There was a lot of debate within our teams, along with our designers and our project uh, people, about whether at all we should carry out a trial assembly. And if at all we carry out a trial assembly of a structure which is 467 meters, where do we find the place in the mountainous terrain to do this erection? Lot of brainstorming extending into late hours happened, and finally we came to a solution, which I will explain in the further slides. But first and foremost, we decided to do a mock-up of the arch in a scale of 1:10 to understand what sort of tools and tackles and enabling works that we will need to incorporate in the process, so that it will be very easy for us to erect the arch segment, bolt it, and also maintain its geometry. With this sort of a study on a scale of 1:10, it gave us the confidence of building upon it on a larger scale. This is one critical component of the arch erection methodology. The second part was that we looked at trial assembly in a laid down condition. I will explain what the laid down condition means in the next slide. It was also done so as to accommodate two modules of wind bracing at a time. This was critical because the place that was available at the location was not adequate to completely erect even half the arch in its totality. But all these precautions and trial assemblies which we went through, which I will explain, actually led us to do finally what I would call a flawless erection of the arch, leading to its successful closure. So what I call as a laid down assembly was the figure on the top shows as constructed location of the arch. But when the trial assembly was done, it was rotated so that the handling would become easier, and the trial assembly was carried out in a laid down condition. The trial assembly was also carried out for two modules. You can see module 1, which is approximately about 40 meters. Module 2, again, approximately about 40 plus meters. The joint between the module 1 and module 2 is the place where the wind bracings are ending. We decided that the trial assembly will be carried out on a plan area of about 90 meters by 50 meters, which we developed near the top of the bridge at the right bank, and we used this space to do this trial assembly. Module 1 and module 2 were first erected. Subsequently, module 1 was dismantled and moved out and sent for painting, for sandblasting and grit blasting and painting. Module 1 was then moved back, and then module 3 was erected, and we continued to erect it till we reached the crown of the arch. This we did both for right bank and left bank next to each other, and hence this complete trial assembly gave us a level of confidence that we would definitely be able to erect the arch in its final form. This was the second key parameter, I would say, to achieving a flawless execution. Some photographs of this trial assembly. You can see between the top and the bottom chord of the arch, the distance is nearly 9 meters. So it's a large enough dimension. We used two EOTs, one for the left arch and another for the right arch, to erect it, so that parallelly we could do the trial assemblies. You can see them happening. These are the wind bracings that are put in place once they are erected. And once these are erected, they were dismantled after the module 2 was put in place, and the geometry which was required in an unstressed condition, that is stress-free condition, was achieved with whatever geometry control points marked on the erection. It was later dismantled, sent for grid blasting and paint. Another view of the same. You can see the complicated angle of the wind bracing, three-dimensional joints in the middle. I will show you some more clean photographs of this at a later date. Now we'll go into the next part of the criticality of an arch, which is the lifting of the individual arch segments. It is not out of place to mention here that the arch segments are inclined inwards with an angle of about 4.2322 degrees. In the vertical plane, the arch segments are varying from an angle of nearly 52 degrees to near horizontal in the center. The segments also needed to be lifted by the cable crane in as nearly as possible to the design inclinations, so that with a minimal effect, the erection of the segment can be completed. As I explained previously, we had 1,375 components, but the total number of lifts by pre-assembling some of the components based on the weight and the capacity of the cable crane was reduced to 944 lifts. The reason being, as we dived deep into the project, we came to the conclusion that in order to do a safe erection of the arch, there is a great amount of enabling works and platforms which will give access safely, and that itself was amounting to 378 lifts. So in order to reduce the load on the cable crane, we had tried to combine some of the arch components to 944 lifts, so that the total lifts would still be around 1,300. These are some of the photographs of the segments of the arch being lifted. You can see that at the beginning, it is at 52 degrees. And as we go towards the center, it was nearly horizontal. This was the methodology used. Here, I would also like to say that thanks to our consultants, right from day one, they started working on 3D model using Tekla. We were also asked to get ourselves fully trained and equipped by using Tekla models. So we had a good team within the project team who were competent to handle Tekla model. And using the Tekla model, we were able to determine very accurately the CGs of each of the segments that we were planning to lift, and were able to derive at the different lengths that we needed to use with adjustments for the different slings that were used. This was, I would say, the third critical event, the planning of the segment lifting and the detailing and the lifting for each and every element of that 944 lifts. Here you can see some photographs where you can see the wire rope slings, the web slings, some lifter beams to assist in the lifting, chain pulley blocks to adjust the micro-millimeter changes that we needed to do, and the polypropylene guide rope, which forms one of the key in ensuring that the material doesn't sway as it moves to the location with the cable crane. Another view of the lifting arrangements, two different types of lifting arrangements that we used with the cable crane. Now I will come to one of the most important components of this erection, which was the wind bracing. In the trial assembly, I had shown you that the wind bracings were erected, and the length of this wind bracing was approximately 40 meters. But to carry it, you can see from the location to the place where it can be fed into the cable crane was itself a challenge. Second, the arch at the beginning had a width of 35 meter, and at the crown it almost reduces to 99.5 meters. The wind bracing had gussets in 3 directions. So geometry was a big challenge for us in this. So once the trial assembly was perfectly achieved, the pipes were all dismantled. They were made individual. And then, just to show you the complicated photograph of the location at which these gussets are coming, again, if you see on a typical central joint, there are 116 HSFT bolts, again with that same 2 mm clearance, and we were able to achieve it with no imperfection. And you can see how snugly it has fitted into this system. This also was because of the trial assembly and getting it all resolved before it actually went to the site. Also, transporting these pipes after they have been trial assembled, grid blasted and painted was a challenge. The road from the place where it was trial erected to the location where it can feed the cable crane was a very, very steep incline. This road, while it did not only carry this pipe, which was a far lesser weight, at one stage also needed to carry the superstructure that was erected from P80 towards 120, which was weighing nearly about 140 tons. So a lot of thought process and decision on getting the gradient of the road right, the material to be used on the road to get the right traction for our prime mover to be able to pull that 140 ton on an SPMT to the location was actually done on paper first as an enabling work, executed at site so that the operation became very smooth. This is a photograph of one of the pipes being moved to the location with the help of 2 cranes. Most importantly, in the third or fourth slide, I had shown you the location of the pylons of the cable crane. This is a berm which is at the one of the foundations at the top. And berms were used very innovatively to stack these materials. No doubt, the excess load on the berms was checked from a load point of view so that we don't have a problem on any of the berms in discussions with our consultants, IISc Bangalore. So adequate precautions were taken. And these berms were used innovatively to stack the material so that the cable crane can continuously work and not wait for the material to be transported to be within its reach. You can see this photograph where the wind bracings, both 40-meter long, are lying, ready for erection. This is another view of the cable crane actually lifting it and taking it to location. And most importantly, what this photograph shows you is the safety features that we incorporated in the enabling works. The blue parts of this photograph clearly distinguish the enabling work from the permanent work. You can see that the worker is having a safe access to each and every point where he needs to work. You can also notice that on the already erected arch, there is a ladder with a handrail that is provided, which is a permanent feature of this arch, which was constructed along with the segment itself, so that it gives access to our workers to reach each and every point. This is another view of the erected arch and the segment and the wind bracing. You can see the height at which it is erected. This is about 52 degrees. I will now take you into the global erection of the arch. When we look at global erection of the arch, we started the arch erection from the foundations, both at Katra and Lavalehan, the right bank and the left bank. The base modules were installed. Separately, I will explain the base module and the geometric control that we did on the base module in a little later. But before that, let's go into the global erection. So we started with 30-ton working loads from the cable crane. The cable crane was used to start erecting the arch segments. After a certain element of the arch was cantilevering, which was about 70 meters, the first of the forestay cable and the backstay cable were put in place, and they were stretched appropriately as per design requirements. Geometry control was ensured here, and later we moved to the next portion of the erection, installed the next set of stay cables, and similar fashion we went ahead with erecting certain part of the arch, again putting cables and holding it back till we reached a level where we were close to closing, and that's where we stopped. This particular part, arch closure, I will explain separately. This is a photograph of the closed arch as it looks, but we will separately have a small this detailing of how this arch was closed. This is global erection in its totality. So once the global erection is completed, that's not the end of the game. We needed to remove these temporary cables. So all the temporary cables were removed, which in itself was a project at that height and at that weight. And once they were removed, then we were able to go to the next process. One point I would like to share here is the stressing of the temporary cables itself had a lot of sequencing to be developed. Here, I would not be hesitant to say that as these cables were being stressed, there was such a great and very, very helpful interaction with our client, with our consultants based out of Finland and Germany. They were available to us, I would say, nearly round the clock, helping us as we did the stressing and ensuring that we were able to get the perfect geometry as we move forward. The stressing sequence was, first we started with the backstay. We did 25%. Then we did the forestay, which was for two cables, 100 for the first, for the middle ones, which was 50%. Then we went back to the backstays and increased the force to 75%. Then we went to the forestays, increased the stressing to cable number, the outermost cables to 100%. Then we moved in to do 100% on the backstays, and then moved into the inner cables to do a 50%. So there was a constant movement of this stressing from inside and outside, but all the stressing was happening on the temporary pylon, both on the left and right. So the movement of these pre-stressing equipments was minimized so that there could be good saving in the time. Now we will come to the most important part of the project, which is the geometry control. And I would like to share with you the most important part was the springing point of the arch. That is the point from where the arch takes off from the concrete foundation. Huge amount of effort and concept and brainstorming was carried out to ensure that the base plate of the arch was embedded in the concrete foundation to a great level of accuracy. No doubt, our past experiences of providing template and bolts for very heavy foundations like turbines did help us evaluate various methods. But the challenge here was that this complete template, if you see, was at an inclination. So we developed a template. This template had a lot of shear studs at the bottom. It also had bolts coming out through it. And this full thing was embedded in the concrete with 6 geometry control points at the top and 6 geometry controls at points at the bottom. And we imposed on ourselves a tolerance of 5 mm, handling this weight of 10.8 and using a lot of time and precision to get this position. In one case, it took us nearly 2.5 days to fix this base plate. But the end result can be seen on the right side. While I would say we did not achieve our tolerance, self-imposed tolerance of 5 mm, we were very close to it. In fact, I would say we had achieved in most places except in 4 places, which you can see in red, which are just about a millimeter or 2 millimeters away. But this, I would say, was the fourth key point in the successful closure of the arch, the geometry control of the springing point of the arch. So with this sort of a tight tolerance, we started erecting the base module. This is the base module that is being positioned. You can see the template at the bottom with a lot of rods sticking out. These base modules will get fitted into it. And subsequent to that, the gap between the base module and the template was grouted with a multi-metal compound, which can fill gaps up to zero 0.1 millimeter. The intention being that the arch is a compression member, and it was a requirement that the arch be completely under compression and have full contact with the foundation. And so extra care and precaution in geometry, in fixing the base module and in ensuring 100% contact was ensured by these methods. This is another view of the erected base module, which you can see. You can see the safety access ladders that are provided all around, including the walkway. They are fully at an inclination. And then there was further geometry control that was required to be carried out as we went subsequently with the arch erection. So some of the things that we did was that the designers, in discussions with us, we had 2 workshops in Stuttgart where we worked closely with them, and we came out with a set of geometry control points. And for each of these points, they had given us the theoretical coordinates at a baseline temperature of 20 degrees. Most importantly, and sometimes what is missed out and could lead to big issues, is the second bullet point here, that is the baseline construction loads. These workshops between Afcons in-house enabling work team and the consultants, Leonard, Andre and partners and WSP Finland, each of these construction loads were positioned. These were detailed in the model by the consultants, and based on that, they gave us the theoretical coordinates, which was used by us when we started erection. So a lot of work went into developing the coordinates and the measurement of the coordinates. Temperature correction values are also provided so that as the work in the project progresses at different temperatures, we can measure the coordinates, make the corrections based on the actual temperature, and proceed ahead with the project. You can see some of the survey points that were put. When it was close to the shore or to the bank, we used just a sticker, which was a luminescent sticker with a point. But as we proceeded further away, you can see on the right the survey sticker in the next slide. But as we moved further away, since the arch was going inside and the visibility was becoming a challenge, this point was pulled out by means of a vertical member sticking out with the sticker put on top. And the total survey was controlled by a total station. 2-3 fundamental things we ensured. We ensured that these points were the points that were on the drawing board, and hence we were measuring the coordinates of the same point which was given to us by the consultant. Second, and most importantly, all the survey work was ensured and done before 8 a.m. in the morning so that there is no temperature impact on the survey. And the temperature at the time of survey was also recorded so that we could cross-check it at any given time. Ultimately, these precautions, these workshops actually was very helpful because it ensured a flawless erection of the arch in its entirety. Some of the tolerances that were provided by the consultant was in the vertical, horizontal, lateral. They had given us a constant of 233.5 mm. I will just take you through the next 2-3 slides quickly. Vertical position, below the theoretical, above the theoretical, horizontal position as can be seen from the drawing, and then the lateral position from on the plan view. So all the locations they had given us a 233.5 mm, but with the tight geometry control that we were able to achieve, and with the other things which I told you, the 4 important things like trial erection, like assembly before, all which we did, and the survey, the base module fixing in correct location. Ultimately, this was the formula on which they had given us the tolerances. What I would like to point out here is that the X2 is a very important phenomenon. As the length increases, the tolerances were being increased or were being permitted to be increased, but our intent was never to go to the tolerances. So with this sort of a control, we achieved these tolerances at the end when just before closure of the arch. You can see the vertical tolerance provided was 100.4 mm. The tolerances in the direction of the bridge was plus minus 50 mm. The tolerance in the lateral direction was plus minus 100 mm. But you can see that as per the figures that we have, we were well within them in these tolerances, which are actually listed by red arrows at the edges of the arch, which are standing freely erected. This was the geometry control parameter sheets that was developed. A close monitoring of this was being held not only at project site, but at all levels, including our head office level. And this data was being constantly shared with our consultants. This is a larger view of the monitoring that was being done. You can see that the temperatures were being recorded. The date was there, the time when it was done, the distance from the arch base, and the coordinates in all X, Y direction and Z direction, which are measured, are recorded in the drawing itself so that there are no errors or no communication gaps between the different parties. Such tight quality control and quality assurance measures ultimately proved that it was possible to build this arch to the dimensional tolerances and accuracies which were demanded of this structure. I will go to the most significant part of the arch. We will look at arch closure. When we have actually erected the arch, it would not be out of place to mention here that the arch would be cantilevering nearly 230 meters from each side. So it would have its own dead weight deformations and deflections. Also, there would be a certain amount of lateral misalignment. So we had to then have a discussion even before, much before this closure, and the methodology was worked out. What I'm going to take you through is the different steps that were involved in the arch closure. First and foremost was to make the corrections in the lateral or the transverse correction. You can see the arrows indicating a 49 millimeter and a 32 millimeter. So we needed to align both of that. These cross members in the photograph, which is blue in color, was used. horizontal jacks were used, and by using the jacks, this segment was realigned to achieve 16 and 8 mm corrected transverse alignment. So the jacks were operated in order to get this transverse direction corrected. Once the transverse direction was corrected, the jacks had the arch free ends had to be lifted up to remove not only its deflection but to reach its correct levels. And the force was calculated based on the final survey data by our designers and provided to us. So in this case, 2640 kilonewton of force was applied between EB30 and WB28, one against the other, thereby lifting the bottom chord of the arch. This is how the force was applied as shown in the red arrows, and this enabled the arch to be lifted up to about 415 millimeters, and the gap also subsequently increased from 5891 millimeters to 6306 millimeters, which was the geometrically correct gap that was required. Once this was achieved, there was still some fine tuning done to get a millimeter accuracy. A tripod was erected and a force was applied in the direction that is shown in the red arrow. This was very small force, and this enabled us to do the fine-tuned adjustments of the bottom card and get it into the correct geometry. Once this geometry was achieved, the measurements of the prefabricated bottom member with one of the splice plates on one side not being drilled was brought to location. It was lowered in location and the splice plates were rotated to take the markings of the holes already provided on the arch. It was rechecked for accuracy and it was found that it was within millimeters. So it was withdrawn, taken to the shore, the splice holes were drilled, brought back, and then it was subsequently lowered and installed. And this was the segment EB31. So here, the only small thing I would like to know is that the splice is both on the left and the right. So the splice would have two sets of pairs of holes on the right, two pairs of holes on the left. The left holes were pre-drilled, the right holes, one side was pre-drilled, the other side was kept free for taking a proper measurement and ensuring that it got properly fitted. But even in this case, we were within the tolerance of 2 millimeter. So this closed the bottom card, but that is still not the end of the story. After the bottom card was closed, the vertical bracing, the diagonal bracings, and which were to support the crown element were fixed in place. Then the crown element, which is ET 30.1, was put in position. And once the crown element was installed, the element between ET 29 and ET 30.1 was fixed. After fixing this, again, there was a need to see that the top chord geometry is as per theoretical geometry. So none of these bracings were fully tightened. A Y yoke was installed, as is shown now in this photograph in blue color. And using this Y yoke, ET30 and WT47 were pushed against each other to again ensure that there is a small rise and the gap as required from 5498 was made 5603, which was the theoretical requirement. Once we reached the theoretical requirement, similar thing as was done in the bottom chord was repeated, and this segment with the final hole all drilled is now being lowered to achieve the arch closure. With this, we were able to successfully close the arch on 5th April 2021. Let me now take you through the challenges, because all this seems easy once the work is completed, but there were challenges. So some of the safety challenges were need to do safe access to the erection point from the base of the arch to each and every location of the arch, secure and stable working platforms at erection point, ensure that under adverse weather conditions and wind speed we do not carry out work, and since all activities were happening at 50 meters, we needed to not only train our people, but adequate advanced life gear systems were to be deployed to ensure that there is a safe work. As I said, there is a huge amount of enabling stable platforms that were involved, which was nearly 300 plus lifts on its own. Adverse weather conditions were being monitored by getting daily weather reports for the day and for the next 3 days in advance. Wind speeds were monitored not only with anemometers at fixed locations, but also by handheld anemometers, so that whenever the wind speeds were increasing beyond permissible limits, work was discontinued, which resulted ultimately in a safe working. These are some of the fixed lifelines that were used. Uh, we did a lot of work on it, uh, and we were able to locate good international parties which could supply these lifelines. We used these lifelines successfully, and we were able to see that even if a person slips, he will not fall down, because each of these lifelines can take a load of 23 kilonewton. These are other safety features. For example, you can see there was a very easy seating arrangement suspended. Not only that, though he is suspended, there is a retractable safety device that is hooked up to his rear, so that even if that suspension seat sling slips, he would still not fall, because the retractable holding fall arrestor would help him in safe working. You can see that all the workers are being safe when they are working at these different areas. This is another view of all the scaffolding. This is a view where even the scaffolding was inspected on a daily basis to ensure that everything was in order before people were permitted to go and use it. And ultimately, the result of all this was that the National Safety Council of India, when they reviewed this project in its totality from a safety, they thought it appropriate. They normally have platinum, gold, and silver as the awards. They felt that the quality of the safety measures taking in erecting this most difficult and iconic arch called for something greater than even this platinum and gold awards. So the jury were kind enough to award a special jury award, which they called the Ati Vishisht Suraksha Puraskar. The maneuvers that we had without any lost time accident from January 2019 to December 2019 was 3.99, and till date from January 2019 is around 8.2 million maneuvers in this arch area. Next, we will go to the challenges that we faced during the arch erection. One most important backbone of this erection was the cable crane. Unless the cable crane was working, no work could be possible. I would not hesitate to say that the cable crane suppliers from Austria were very, very cooperative with Afcons in ensuring that they were available to us whenever required. And not only that, they had set up a remote diagnostic feature in the cable crane, so that any minor issues, and we communicate to them, they can access this remote device, find out the problem, give us solutions, so that immediately we can get it repaired and put it back into operation. So some of the safety features was already incorporated in the cable crane. Second was that lightning arresters were erected so that the cable crane and its operators were safe. Critical spares, including one engine for this cable crane, was procured and kept. Incidentally, the cable crane is driven by a very popular engine, which is now doing wonders in the F1 racetrack. It's from Mercedes, and it did a fantastic job for us on this project. Working at heights and ensuring safety was another key feature. All our engineers, and I want to repeat here, it was not only the workmen, even the engineers were given extensive training in working at heights, because each and every bolt location where HSFG bolts were used, the need was to ensure that the right torque and the right sequence of torquing was applied, and it needed a quality assurance. So engineers were required to go to each and every location where the workman was going. So they were also trained in using and working at safe heights. Temporary structure erection also was a challenge. It was time taking, but with a disciplined team and dedicated team, the challenge was handled successfully. As I have already explained to you, the trial assembly of the arch segments was the backbone of this project's successful closure, and the transportation and the erection of the wind bracing, which I have explained to you in a few slides before. Tightening of the HSFT bolts was very crucial. A combined method of torquing was adopted. A detailed method statement was prepared in discussions with our consultants for installing the HSFG bolts. And while these are all on paper, it is important to say that it was meticulously followed by the project team to ensure that it was followed, it was documented, and it is even available today as a documented part of the project. Here, I would also like to tell you that each and every component of the arch, be it the bolt, be it the steel plate, be it the bracing, have a unique ID and a traceability, and these records are available for the future as a well-documented literature. Considering that the work was happening at very great heights, specially imported lightweight battery-operated torque wrenches were procured so that there was ease of working for these workers working at height. These were some of the challenges and what we did to overcome it to erect the arch. Some key factors to summarize, I would say, is detailed and meticulous planning. Lot of workshops were held at different stages of the projects. A lot of midnight lamps were lit. And I remember some of the workshops where we even worked up to late 1 o'clock without even realizing it's midnight. That was the passion and the attitude each of the engineers who were at the project, including our consultants who brought on the project to make this a success. Trial assembly and trials and mock-ups definitely helped us. Continuous coordination and communication with all the agencies across the globe was another factor for the key success. And last but not the least, a big, great thank you should go to the team leader who led the team by example, well supported by his team, who rose to the occasion and delivered this project flawlessly. With that, I come to the end of the presentation. There is some small thing which I want to share with you about the balance work, because the arch closure by itself is not the end of the project. Post closure of the arch, we need to first concrete the boxes. Presently, the work of concreting is in progress. There also, needs to be a meticulous. We cannot just keep pouring the concrete. There is a rate of rise that is permitted, and we have to stick to those parameters. Then the trestles would be erected. And once the trestles are erected, the incremental launching from both sides would happen, and that would meet at the middle and the crown. And once it meets at the crown, the bridge would be ready for operation. Thus, what was seen as a challenge will ultimately turn into a marvelous piece of work. So, gentlemen, thank you very much for giving me the opportunity to make this presentation to you. I am now opening the floor for any questions. Mr. Ajit, I would like you to take over. I would say that the floor is open for questions, permitting time. If time is exceeding, I think you can send your queries to ICE, Mr. Rajesh or Mr. Ajit. They can in turn send it to me, and I would be more than happy with my colleagues' help to respond to each and every question. So thank you very much, Mr. Ajit, and thank you to ICE, and thank you to all the people who have spent nearly an hour and 15 minutes patiently hearing my presentation. Thank you very much. Over to you, Mr. Ajit.
Yeah, thanks a lot, Mr. Giridhar. It was really a marvelous project and definitely one of the new wonders of the world. And it's our privilege to really look at this presentation. I know that you made, like, you sort of shown everything about it, but you made this so simple. But this is really a very complex challenge that every civil engineer should be proud of. Definitely, there are few queries we'll go through very quickly. I know we are running a little over the time, but for such a marvelous job, few minutes over time doesn't really matter. One of the questions that has come in is you mentioned about this design life is 120 years. So how this like 120 year and what?
Mr. Ajit, your question was how was it designed for 120 years, right?
Yeah, that's right.
Okay.
Like what precautions were taken or what considerations were given?
Okay, let me tell you first and foremost, the detailing, the ductile detailing and the fatigue design, which was ensured of the highest order, was brought into the design element itself. Second, the elements were then, for example, these bolts in India, geomet bolts, was to ensure long durability of the bolts. Third, the accessibility, there is a separate presentation which will itself take 30-40 minutes. Each and every area of this erected bridge can be inspected and can be repainted as a part of its maintenance. The paint itself was selected to ensure a minimum of 15-year life, and repainting possibilities were worked out and detailed into its maintenance manual to ensure that there is durability. Last but not the least, some of the cable anchors which I told you and the bolt anchors were designed with double corrosion protective measures which gave it an assured life of 120 years. This in a nutshell answers that question, I hope.
Yeah. No, certainly, and I believe that design life is 120 years. That is a minimum 120 year. This bridge can withstand even the sort of 240 years also, because it's only designed with a minimum life of. It can go on forever. Forever doesn't mean forever, but I'm sure that you must have chalked out a very detailed maintenance plan for this kind of a structure, which also could be very complex and challenging.
You are right. As a part of our contract closure documents, we are supposed to hand over to the clients a maintenance document with the operating procedures for the different maintenance equipments which will be installed on the project.
Yeah.
Definitely, let's say in India, you can see Howrah Bridge. It's now been standing for quite some time.
Yes.
And I believe one of the other benefits of this area is that it is not a very highly corrosive environment. It's up in the hills.
Yeah.
It is at the moment, pollution free. And so we believe life from an environmental perspective would not be a challenge if it is properly maintained regularly.
Exactly. One of the questions or queries that has been asked is because this is one of the kind of bridges in India. So what were the codes used for design?
Basic background was BS code, supplemented wherever required by Euro code and IS codes.
So the combination of various codes to arrive at the most optimum design.
I would not say most optimum. I would say a design which was durable
Yeah,
and which was robust.
yeah, yeah. That's absolutely true. Certainly, like when we have achieved so much, uh, it's a really a satisfying moment for you. So what was the sort of most challenging part, and what satisfied you the most? Because this whole thing is definitely satisfying, but within that also, what was the most satisfying thing?
See, for a parent, it is very difficult to choose a child.
Exactly.
In this context, it is very difficult for me to choose one moment in the project.
Yeah,
I call this project as a temple of the new age of construction. I
I would
repeat, I call
certainly
it as
agree. Yeah,
temple
I would certainly
of
agree with
the
that.
new age of construction. Example, I was elated when we finished the increment launching on the transition combined curve
Yeah,
because this was never done. And we developed the in house methodology to successfully launch it. And when we achieved it, and then I got a feedback that, sir, we have checked the bearing locations and we are within a 5 millimeter tolerance. That was one point of elation. The second point was, but then we cannot rest on our laurels. The next challenge were already looming ahead. The other section of the viaduct was coming close, and we were hoping we meet each other properly. And when they told me, sir, we have been able to come close to each other, the difference is laterally only 3 mm. That was the second level of elation. Again, when we were quite successful in erecting the base of the arch, it was a point of thrill. So let me again reiterate and say, like a parent and a child, this project has a number of childs, and I'm sure over a period of time, I would be happy to go back and think over it and share it with my grandchildren at an appropriate time.
yeah. No, exactly. That leads to my last point. Again, what were the lessons learned, or if there is anything that you would suggest to your grandchildren to do it differently if they have to reconstruct, or not reconstruct, but replicate a similar bridge elsewhere?
To be honest, at this
Nothing.
juncture, we are
Nothing.
all looking at closing this bridge.
Exactly.
We haven't taken a step back to look at lessons learned, though in different forums with different teams, they have been documented.
Yeah.
A total sitting together with our knowledge services group. We have, and I also head the knowledge services group for the company.
Certainly.
Our team has been capturing different elements of the project and different learnings.
Yeah.
It is too premature for me to tell you in one nutshell what we would change unless I have a global view of the project once it is completed.
Exactly.
I would be more than happy to share with the industry once we have completed the bridge what we could have done better. Because, as they say, benchmarks are set or world records are created only to be broken. So,
Exactly.
I would definitely share all this at an appropriate time.
Sure. Certainly, I think looking at time, I think we'll close this queries. But as it was earlier discussed, if you have any query, please feel free to write to IC, either Rajesh or me. Our coordinates have been sort of provided. So Mr. Giridhar, I would really like to thank a lot. Particularly, there are no words to explain how grateful we are for such a fantastic presentation. It was really a marvelous project, and your passion, and you correctly described this as a relation between your parent and a child. And unless you have a passion like this, we cannot really succeed in any project. Uh, but this was such a marvelous presentation, and I'm privileged to really see this a presentation, and that sort of inspires me to really look for more and more challenging roles, as well as to go and see this bridge live, and just appreciate the work that you have done and the Afcons team. We really appreciate, and looking at the comments, I think everybody is appreciating you and Afcons team for constructing such a marvelous structure. with safety in mind and with all the maintenance and everything in mind. So from ICE, really thankful to you.
I have one small request.
Yeah,
I would be very happy if the people who attended this lecture share through you
yeah,
their views and their constructive criticism to enable not only me but Afcons raise the bar in the presentation also.
yeah,
It would be highly appreciated if we get this feedback.
yeah. And when I was looking at some of the participants, I see some of the really stalwarts in bridge construction and structural engineering in the audience. So I would encourage the bridge experts and people to provide comments. I would certainly like to thank all the participants, and we really had a great response to this. Like we were almost around 140 participants, and as Rajesh explained, it was uh, covering almost 21 countries. So that itself is an achievement for us. So I would like to close this thing with a really a heartful thank from everyone who has attended, and also the AFCON teams. So thanks a lot everyone for joining this session. We will soon look forward for the next session of ICE very soon. So
Thank
keep
you very
watching
much.
ICE space. We will sort of have similar session. Thanks a lot.
Thank you very much.
Thank you.